think my latest recommendation people don't talk about yeah, I was. Yeah, it was like the last thing I saw before I left.
If I just shoved it in my bag.
You have what, 2 full races and 3 reverses? There. That's not, it's supposed to work. It's not supposed to have more reverses than you do not. It's just not.
You got 10 yeah, we have.
Way better.
No, I don't even have.
Was this time or last time?
Oh, I
Yeah.
have 2 full indexes. And one of them I use stupid strategy. There used to be a thing where people would create brand new accounts, like on mass. And then they would have a single pack, like Amazon Black Pack.
So much
And then
information.
just program going, and you friend them, you can take my pack and then you pick no matter what. So I did that once, and I patched it today.
School business.
They really do.
Brendan, data
Like climbs them all on like the mathematics side of work.
Oliver.
You got me scared there. You know what, you have what, the immersive Mewtwo, immersive Dialga, and immersive Celebi?
I would not say maybe not at this time, but just at this one. Yeah, here. It's too big. Oh,
Oh, I couldn't get one more.
this is the
Dude, like, this week I haven't gotten a single, like, I haven't gotten a single That's how it probably was when you first started. I've finished most of the solo battles for these left of the export ones.
Okay, I know most of you guys already turned in assignment 62, but if I don't have yours yet with your name on it, make sure you're getting that to me here. Bell's about to ring.
Actually, go and release that section. Most hating on the
God, yeah. That's all our problems. It's all.
All right, last call. Any other 62s?
It isn't hard enough to sell it. It's hard to sell.
She wants to do that.
I've only lost one time, but 4 or 5 years. I need to. It really is crazy, especially since I do that over and over and over. You get to try well, I got really close.
Thanks very much. Will you please stand for the pledge?
Well, if you're
To the flag of the United States of America, and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Thank you very much. Have a nice day.
Okay, if you came in late, you need to get me your number 62 for full points here in the next minute, please. Okay, so as we are down to about 5 to 6 topics, today we are finally getting into one of the more famous BC topics, which is called Taylor polynomials. And some of the rest of the stuff that we'll be doing in some of the other sections will be kind of similar to this, but this one does have a little bit of a different take to it. It's less about infinite series and converging and diverging, and instead trying to basically come up with polynomial functions. And the reason why polynomial functions is because they're just easy to work with. Polynomials are easy to do in calculus, easy to take the derivative of, easy to take the integral of. There's also a type of polynomial called a Maclaurin polynomial, and that is just a very specific Taylor polynomial. So we'll be talking about both of those today. So first, if we start looking at this function over here, so we can kind of see what we are trying to do. What you would have done in AB is, let's say we're talking about some value at C, x equals C. In AB, the only real approximations you would do for a function is a tangent line approximation. So you could plug this point and this slope that comes from the derivative into point slope, and this is kind of a visual for what's happening at x equals C. But if I'm trying to come up with a polynomial that estimates this function, that's a terrible representation. This compared to this, they're just wildly different. So we will talk about, so if we say the function at C, we're going to call that P of C. And the reason why we're going to talk or use the letter P in all of these is P stands for polynomial. Again, we're trying to estimate these as a polynomial. And oftentimes, we're going to use this terminology. We're going to center it around C. The function centered at C. Another way to say that is we're going to expand the approximation around x equals C. So basically, we pick an x value, and then we kind of work off of that to make a good estimation. So what would make this a little bit better than just a linear line, just knowing a point or the y-intercept, whatever, and the slope, what we will be doing is then we'll think, well, what about if it wasn't just linear? What if we looked at something that was like quadratic, a quadratic approximation? So at x equals C, a quadratic starts to look much better. Well, at least this side does, because at least it fits this pretty well. So it's kind of a combination of linear with quadratic with exponential, that we just add these different terms together, and you'll see that they get to be pretty accurate pretty quickly. Okay, so using this example, let's let C be at x equals 0, and this is the function e to the x. Okay, so what we want to do to come up with a polynomial, Taylor polynomial that's really an approximation of this real thing, because e to the x is not a polynomial, it's an exponential function. So one thing we'll make sure that we have the same as is that it's got the same y-intercept. So whatever the y-intercept is of the real function, f of 0 would be 1. We need our Taylor approximation to also be true for that. When we plug 0 into our estimated polynomial, it needs to also return a value of 1. That way, it's like we're starting there. Okay, at this value, we could have, so if we simply think of the slope, we go from having a point, which is nowhere near this function, to if we also include the slope, now it's starting to get a little bit closer. My blue line is closer to e to the x than just the red dot. So we also need to make sure that not only are they at the same point at x equals c, for this example 1, 1, they're both there, but at that time they also need to have the same slope. So the derivative at c needs to be the same as the derivative at c for our estimation. And then for this question, we could actually plug in 0, because we're saying c is 0 here. So ideally, we start them at the same point, like the y-intercept. Then we make sure they have the correct slope, first degree. So then it's got the right slope at that moment. And then as we keep adding pieces to this, it'll get more and more accurate there. Okay, so this is what we call a first order approximation. What is first? You may not be as familiar with the word order, but what does order also mean?
Lack of chaos. Structure.
Okay, the mathematical definition. I hear you, I just can't hear.
Degree.
All right. Order just means degree. So if we can estimate it to the first degree, this is what's called a first order derivative. So to come up with this line, we could simply just start off with point slope. We can say we've got the polynomial here, subtract the actual point, which is f of c. The slope is going to come from the derivative at c, and then this is x minus the x value of this point. So for us, that would be 0. And then if you add this over, a first order of this would be the derivative times x minus 0, and then add over the f of c. This is a polynomial function, and it's considered a first order approximation because this would have, well, if we actually plug this stuff in, because we can actually find this derivative and plug these things in. If we actually plug this stuff in, it would just be that, which is degree 1. So that's what makes it a first order. So we can make this more and more accurate, but that's the basis. We make sure that it start wherever we're centering it around, that they have the same y value. That's like this. Then we make sure that they have the correct slope at that time. But again, we can make it even more accurate by using the second and third and fourth derivative to get the second, third, fourth approximation. Okay, so improve the approximation. We can do the second derivative at x equals c. So if we kept doing this, the second order would be the same as this stuff, plus that. Now I'm going to show you how to come up with that. But this, if you graph this, all of a sudden it starts to be a much closer, starts to be a much closer approximation. Let's see if I could graph it very quickly here. So in my calculator, it shows me it goes through this point, which we did. It kind of does like this, and then it kind of does like this. So a second order is also not a perfect representation, but you need to see as we add layers to this, we started with the point, was nowhere e to the x. But then we used the first derivative to make sure it had the right slope at that time. This linear line is still pretty far away from e to the x, but it's closer. Then when we add this second order approximation, which I'm going to talk about on the next page, when we add this part to it, it gives it some quadratic curve, and you can start to see it starts to get pretty close to e to the x pretty quickly. So even after just a quick couple ones. Okay, so on the next page, you need to know that anytime it says Maclaurin polynomial, that means it is centered at 0. So again, it is a Taylor polynomial approximation, but it's the specific one that's centered at 0. I tend to like these because if you center something at 0, 0 is just an easy number to work with. But here's how we are going to write these Taylor polynomial approximations. The Taylor polynomial is equal to we need to make sure it's at the right point. So if we're centering it around x equals c, it needs to be at the same point as f at c, just like we did on the other page. Plus, and actually go ahead and write this down here too. It's actually over 0 factorial. 0 factorial is 1, by the way. I know you might think it's 0, but it is 1. Okay, so that gave us the point. Then we wanted to know the slope. So the slope at that x value times x, so that it's a slope. Divide that by 1 factorial. Okay, and then actually right here, I should have put this, but since this was 0, oh, I'm looking at the wrong one. Sorry, if it's centered at x equals c, we shouldn't just say x here, we should say x minus c. Okay, so for this one, if this goes from f of c to f prime of c, what do you think is going to be in this third fraction?
F double of C.
Very good, f double prime of c. This was x minus c to the 0. This is x minus c to the first, so this one needs an x minus c squared. This is how far we would go out if we wanted a second order Taylor polynomial, because it gives us a second degree. And what do you think this is going to be divided by?
2 factorial.
2 factorial. Okay, write out what you would just guess the next term is.
F triple prime of c multiplied by x plus c to the third over 3 factorial.
Okay, well, if you came in late and got it right, then the rest of y'all better got it right too.
Nice job, right?
Okay, so to sum this up, so this would be a first order because we would end up with an x to the first. So this is how we would do both of these if we need a first order. If we need a second order, that means second degree, and we'd have to do these first 3 to get to a second degree. You'd have to do these first 4 if you want to get it to a third degree. But we can also say plus dot dot dot. Just a general way to say that is we're going to take the nth derivative of f at c times x minus c to the n over n factorial. So this is the pattern that we're going to use to approximate. Obviously, the more of these you do, the closer a fit it is. But typically, we just go to about the second or third order, just because after that it gets kind of redundant. Okay, so now, if you know that this is centered at 0, if it's more specifically told it's a Maclaurin polynomial, that means that c is 0. So we can write all the same stuff down right down here, except instead of saying c's, we can say 0. Maclaurin polynomial would be at f of 0 over 1, 0 factorial, plus the first derivative at 0 times x minus 0 over 1 factorial, plus the second derivative of 0 times x squared over 2 factorial. Why is this just an x squared instead of an x minus c squared? All right, if it's this type, c is 0, so we don't have to say minus 0. Okay, plus dot dot dot. So we would take the nth derivative and plug in 0 times x minus 0 to the n all over n factorial. So the only real difference between these two boxes is this one is generic and always works. This one is saying if you're centering it at c equals 0, if you're centering it at 0, then c is 0. And so you could plug in 0 for c, and it looks a little bit nicer, I guess.
Will you specifically give us directions to center it at 0, or will we have to decide?
Yes, you have to either be told to center it at 0, or like this next question, they're just going to use that word. When they say that, you need to know that is centered at 0. They expect you to know that. And again, once you do a few of these, you're going to see you are going to prefer these just because 0 is such a nice number to work out with. Okay, so now let's look at some examples so you can see how we're actually going to use this. Okay, so e to the 2x is an exponential function, or a non-transcendental, or not non, transcendental function. But for calculus purposes, maybe we want to write this as a polynomial, because a polynomial is easier to work with. So if I want a third degree polynomial, I'm going to do polynomial, I'm going to put a little 3 here, to state that it's a third degree, or it's a third order. Okay, look up above. What's supposed to give me my first little fraction here? This is supposed to be the point.
F of 0.
Okay, f of 0 over 0 factorial. Now again, 0 factorial is just 1, but please keep writing it because you'll see why I'm going to ask that you do that in a minute. Okay, so that's enough to get it to a first degree polynomial. So we need to add the next little fraction. What's the next piece going to be? F prime of 0, and then what?
Over 1 or times x over 1 factorial.
Right, times x minus c over 1 factorial. This would give us a first degree, by the way, because this is like x to the first. Degree 1, we need to get to degree 3. This isn't a degree, this is just a number. Okay, so then you can kind of see the pattern there, so hopefully you don't feel like you're memorizing those top 2 boxes. The next one's going to come from the second derivative at 0 at times x minus 0 squared over 2 factorial. And then the third one is going to be what times what over what?
F prime of 0.
Okay, times,
X to the third.
okay,
Over 3 factorial.
over 3 factorial. Now, one reason why I'm going to insist that you write 0 factorial and 1 factorial, even though 0 factorial and 1 factorial are 1, what's going to happen is if you don't write these because they're 1, there is going to be lots of times you forget about the 2 factorial and the 3 factorial. That's probably going to be your most common mistake, is you're going to do this and then you're going to forget the denominator pieces. So if you write it like that each time, then it shouldn't be an issue. Okay, so now we can actually find these things. F of 0, I can plug in up here, is just 1. 1 over 1 is 1. So if you graph this line and you graph this line, they're not going to be anywhere near the same thing, but at least they're going to touch at the point when x is 0. So it's kind of like they're starting at the same time. Okay, next I need the derivative at 0 times x over 1. So out to the side, we'll need to do the derivative. Make sure you use chain rule here to get the 2. And I'm evaluating that at 0. So 2 times 1 would be 2. So basically this first fraction, make sure that it starts off at the right y-intercept because it's when x is 0. The second fraction's making sure that you have the same slope as this one at x equals 0. So it kind of tilts your polynomial approximation in the right direction. And then to make sure it has some of the right curvature, we can use this. So I would need to know the second derivative at 0. So take the derivative over to the side. Don't forget chain rule. That would be 4. It gets multiplied by x squared over 2 factorial. And what is 2 factorial?
2.
Okay. And 4 over 2 is just 2. So I'm going to simplify that. And they want us, so you can see that a third order is a little more tedious, but it's not harder. I mean, to do each one of these steps, you just have to apply another layer of the formula. But then keep going. So third derivative, do the power rule. I'm sorry, not the power rule. Don't forget the chain rule. Since we're plugging in 0, we get 8 times 1 over 3 factorial, which is 3 times 2 times 1, which is 6. And I'm just going to reduce that to 8/6 to 4/3. Okay, so let me graph this because I want you to appreciate what this formula is trying to say here. So I'm going to graph e to the 2x for us, and then I'm going to graph 1 plus 2x plus 2x squared plus 4/3 x cubed. Okay, so the blue line is going to be the function we are trying to approximate. The red one is the Taylor approximation that we came up with. So they're not going to be the exact same thing, but we went out far enough to a third order, so they should be reasonably close. So that's what we started with. We made sure that it was at the same point at 0. We made sure it had the same slope at 0. We made sure it had the same concavity at 0. And we made sure it had the same third derivative. You guys remember what third derivative is called? Jerk. So when you do that, again, it's not a perfect fit, but look at this. This part, like about half of the function, is pretty close to perfect, considering we've only spent 2 minutes on this question. So that's what we're doing. And of course, if you did a 4th or 5th or 6th, the higher order you do, the closer your approximation is going to get to the real thing. But that's how you can come up with that. Okay, and then to kind of show you how close, well, I did it by graphing, but if we evaluate f of 0.2, so if I plug 0.2 into e to the 2x, that's about 1.492. And if I plug 0.2 into our Taylor approximation, we get 1.491. So same thing I was trying to get you to see with the graph. This is not a perfect representation, but with as much effort as we put into it, you can see that it's using this point as an example. It's not the exact same thing, but it's pretty close. It's a pretty good approximation, all things considered. Okay, so now let's say this one, let's do this one together, because it's really the same thing.
Yeah, those second parts require a calculator, right? You plug it
This
in.
one?
Yeah, you evaluate.
Well,
Technically, that's
0.2 times 2 is,
0.4. Yeah.
add 1 to that.
What do you do?
Okay, 0.2 squared
0.04.
times 2. Add that to the other stuff.
That's true. You don't need a calculator.
Oh, okay. I would use a calculator, but in theory you could do it if you had to. It'd take you a few minutes though. Okay, now we're going to do a 4th degree. So we're just going to apply the formula one more step. If you kind of understand the pattern of the formula, that's not any harder. We'll eventually need the 4th derivative, which I guess is a little bit more work, but it follows it's almost like those boxes on the top there are just your formulas to come up with what you need. So, fourth degree Taylor polynomial, the first part should be, well, what does the formula say? By the way, this is not a Maclaurin. This is not centered at 0. So the first fraction is what over what? Okay. F of c over 0 factorial. Okay, what is f of c? Okay, 0 over 1 is 0. Now, I'm going to erase that later, obviously, but I'm going to leave it there for right now. Okay, plus, so this is kind of making sure you're at the same point when x is 1, f is 0. So at p of 1, we want it to also be 0. We want them, this is where we're trying to center it, so we're making sure that those are at the same place at the same time. Now, to kind of tilt our approximation in the right direction, we want the slope to be the same. So this is f prime of c times x minus c all over 1 factorial. And in this question, c is 1. 1 factorial is just 1. So I just need to multiply this by f prime at 1. So over to the side, I'm going to need several derivatives, so I'm going to just kind of keep a little running tally here. Derivative of natural log of x is 1 over x, and at 1, that would be 1. Okay, and then down here, I'm going to start to clean it up for my answer down here, but 0 plus doesn't need to be there, and I distributed to 1. Okay, so far, what degree of Taylor polynomial have we done?
First degree.
Good, because we've only got an x to the first. We got to keep going until we get to the fourth. So the next one, it follows a similar pattern here. Second derivative at 1, 2 over 2 factorial, and this will be x minus c squared. This is what makes it a second order, is you need a square on the x stuff. Okay, so we're going to need to know the second derivative. You might rewrite this so you can do power rule. Bring the power down, lower the power by 1, but at 1 that becomes a negative. This is a x minus 1 squared, bless you, and 2 factorial is what? 2. So minus 1/2 times x minus 1 squared. So we've worked up to a second degree Taylor polynomial. Okay, third degree is going to come from plugging in the 1 into the third degree times x minus what you're centering it at cubed over 3 factorial. Again, this is why I'm asking you to write the 0 factorial and 1 factorial. Even though those are 1, it makes you more likely to remember this 2 factorial, this 3 factorial, and then the 4 factorial coming up. So I need to plug 1 into the third derivative. So third derivative, bring the power down, lower the power by 1, and at 1, the third derivative is just 2. So 2 times x minus 1 cubed over 3 factorial. And 3 factorial is 6, and I'm just going to reduce my 2/6 to 1/3. Okay, so can we quit yet?
No.
It says go to 4th degree. I've only done to a 3rd degree. So again, it's a little, the more times you do it, the more accurate it is. It's not really any harder, it's just a little more tedious. So 4th degree at 1 times x minus 1 to the 4th over the 4th factorial. That's the next term. If we wanted to approximate it that much, that's what we would need to do next. So we would need to know the 4th derivative, bring the power down, lower the power by 1, plug in 1 into that, we get a negative 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. And this reduces to 1/4. So piece up those parts, and then there is a 4th degree Taylor approximation for natural log of x centered at x equals 1. So again, if you want to see that this is a good approximation, feel free with your calculator. I'm not going to take the time to do this one, but you can graph the natural log of x as one graph. You could graph all of this mess as a graph, and you can see that they are pretty close to the same thing. But the big difference is natural log of x is not a polynomial. Writing it this way is a polynomial. Polynomials are just easier to work with in calculus. That's why we like to do that. Okay, and then just a quick example to see how close it is. If I plugged in 1.1 into f of x, it comes out to this within 3 decimal places. And if I plug in 1.1 into our Taylor series,
Mr. Townsend,
sorry?
did we make sure to do the 3 factorial and 4 factorial versus just doing 3 and 4?
We did. I just simplified these fractions.
Yeah.
This was actually 2, and this was a 6. So 2 over 6 I just reduced to 1/3. Yeah, you might not want to erase that for your notes. I just didn't want to copy down the whole extra line and take up that much more space. So I reduced those fractions. Sorry, I'm typing them in so that you don't have to, but it takes a second. Okay, and this one came out to be about 0.093. So, assuming you had a calculator for a question like this, although you really don't need a calculator for this question too. I didn't do anything with the calculator and any of that. But if you had a calculator and on the test you just plugged in a random point like 1.1 and 1.1 to see how close they are, does this look like a good sign to you or a bad sign? To me it looks like a good sign. It's almost 3 decimals accurate. Now, of course, that's pretty close to what we centered it at, so close to where we're centering it at should be pretty close, but that's where that comes from. Okay, and then a lot of questions are going to ask about the coefficients. So it'll say something like, what's the coefficient of the, see, how do they phrase it? They'll say something like, okay, well, I don't see, I know there is some, but I don't know where they're at. So sometimes they're going to say something like, what's the coefficient of x squared in this Taylor polynomial? So the long way is you could just say, well, here's the first term, the second term, the third term. This is where x is squared, and then this stuff makes up the coefficient. Coefficient is just the fancy word for what you're multiplying it by. So you can figure out what you need, find that derivative at that value, divide it by that factorial, and you can have the coefficient. Or you can try to use this formula, and I'll just be honest, I don't really use this formula, but I'm sure it is a little more efficient at times. But if you plug in c into that derivative. So this is saying derivative, f to some power. So I can't put 2 tick marks because then this would only work for second degree. So this is derivative at c divided by n factorial will tell you the coefficient. Oh, okay, here, this is a good example. Question 3. So it says, what is the coefficient of x minus 2 to the 4th? If it's a Taylor approximation for f centered around x equals 2, which I kind of already knew that anyway. So what you could do is you could say, well, let me just write out the whole polynomial, which is what we were doing on the other page, which would be like, you know, f of 2, 0, don't write this down, plus the derivative at 2 times x minus 2 over 1 factorial plus the second derivative at 2 times x minus 2 squared over the second factorial plus the third plus, okay, my computer's rebelling. Okay, plus the third plus the fourth, which would be the fourth derivative at 2 times x minus 2 to the 4th over the 4th factorial. And then I could say, okay, well, the coefficient of x minus 2 to the 4th is this. Well, that's really just the same as this formula. So you don't have to memorize this formula more than what we did for the other page. It's going to come from the plugging in 2 into the 4th derivative. So notice they gave us the 3rd derivative, which is nice. So the 4th derivative, bring the power down, lower the power by 1, and then multiply by 8 for chain rule. And then at x equals 2, this would be 16 plus 2 is 18, and that's the same as, I don't know, 36 square root of 2. That's your answer. But 2 ways to go about that. If you want to memorize this formula, then you can just jump straight to the thing that it's looking for. If you don't want to memorize this formula, you should be able to find it from what we did on the other page. I've got the point, the first derivative, second derivative, third derivative, fourth derivative. If I write that out, I can see the coefficient of x minus 2 to the 4th, and I can see what I need. It just happens to be the same thing as the formula. So, okay, so using a lot of the questions are going to be like this first practice question, so I would like you to try this one and for us to go over it, because if you struggle with this one, you're going to struggle with the next one as well. Okay, so this one says come up with a 4th degree. So our answer needs to go out far enough that we get x to the 4th stuff. And because it says this, why is this relevant? Right, it's centered around x equals 0. So c is 0. And you're trying to approximate e to the 4x. So go ahead and try this one. See if you can do the first couple steps without flipping back to the formula to the other page. But when you get stuck, then flip back. And as I said, we'll go over it. So. I'm sorry?
Because I got square root of 18 over 2. This is the 4th factorial.
Oh, yeah, I'm sorry guys, just let me interrupt you here for 2 seconds. I got so focused on just trying to point out this formula was this. This work over here wasn't that. I didn't do the divided by 4 factorial. I didn't do the divided by 4 factorial. This shouldn't have been my final answer. I should have divided by 4 factorial, which is 24, and then that reduces to 3 square roots of 2 over 2. That's the actual answer. Thank you for telling me that. Okay, I'm gonna give you about 1 more minute, which I don't think will be enough time, but you should either be getting close to finished or at least know where you got stuck, so. Okay, so I want to go ahead and started by just writing out the whole formula, even the parts you might not think of, because if you write it this way, which I didn't write it for you this way on the other page, but if you write it this way, you can see the kind of pattern here. We don't normally write this because it's to the 0 power, but if you want to write it to the 0 power, it makes it easier to remember the next one's to the first, second, third, fourth. 0 factorial, first factorial, second factorial, third factorial. So, if after a few of these you're struggling with that piece, you might choose to write it out that way. Okay, and then if we are trying to center this at 0, because it's a Maclaurin polynomial, C is going to be 0. So f of 0, plug that into the function, you get 1. Anything to the 0 power is 1. 1 factorial is 1. So if I simplify this, I just get a 1 from that stuff. Okay, over here, I need to take the first derivative at 0 times x minus 0 over 1 factorial. So I need to plug 0 into the first derivative. So at some point you needed to think about the first derivative is 4e to the 4x. If you just said e to the 4x, you didn't think about chain rule. And at 0, that would be 4. So that simplifies to 4x. Okay, plus, then we need the second derivative at 0 times x minus 0 squared over 2 factorial. So second derivative would be 16e to the 4x. At 0, that is 16. So I'm already up to a second degree. Do it again for the third degree. Third degree at 0. I don't know. 16 times 4 is 64. Over 3 factorial, which is 6, times x minus c cubed. And c is 0. 64 divided by 6 is 32 thirds. So the higher the degree, the more accurate it is, the more tedious it can be, because I'm just doing the same thing multiple times. But if you can do a second or third order, you can certainly do a fourth order, because you just got to do it one more time. So fourth degree, well, I don't know, 64 times 4 is 256. At 0 is 256 times x minus c to the 4th all over 4 factorial. 4 times 3 times 2 times 1. 4 times 3 is 12, times 2 is 24. That reduces to 32 thirds. Is that right?
Yeah.
I'm just trusting my word from the other day. Finally got it up to a 4th degree, so that's how I know I can stop. So obviously, this f of x that we started with and this polynomial function that we came up with are not the same thing, but at 0, they're at the same point, they have the same slope, they have the same concavity, they have the same jerk, they have the same 4th degree, whatever that is. I don't even know the name of that. And so when you make all of those things true about what you're centering it about, it forces this polynomial to be a pretty close fit to that, even though they're not the exact same thing. They're close for our purposes at least. Okay, so I'm gonna give you more time for question 2. I do have the answers posted online, so you guys are welcome to start working at your speed here, but I will offer to go over question 2 with you after I give everyone several minutes. But if you don't end up with this on question 2, you need to try to find your mistake, or you'll need to follow me when I go over it. So. probably half of these practice questions are like this question. So not only will it get easier, it should get much quicker too. Does anybody need longer for number 2? It's fine if you do, I just want to make sure I give you time. Okay, so if you did not come up with this as an answer for number 2 down here, then please follow along with me here. If you did get that, you can tune me out and keep trying. The others. Okay, so I'm going to go ahead and erase this. Okay, so one thing that I think is not a bad idea as you practice, just because it's going to help you remember what you're trying to do long term. Nobody says you have to write out the whole formula, but if you have the formula in front of you, it's harder to forget what goes where and to maybe forget something. So this is a Maclaurin polynomial, so it's going to be centered around 0, which is good. Centering it around 0 makes all of our numbers usually work out a lot easier. So the 5th degree is going to come from plugging in the function at 0 over 0 factorial and x minus 0 to the 0 plus, then this is 1 factorial, and this is x minus 0 to the 1st, and this would be f prime at 0, then f double prime at 0, x minus 0 squared over 2 factorial, plus the 3rd derivative at 0 times x minus 0 to the 3rd over 3 factorial, plus the 4th derivative at 0 times x minus 0 to the 4th over the 4th factorial, plus the 5th derivative at 0 times x minus 0 to the 5th over the 5th factorial. Now again, I don't normally write x minus 0 because that doesn't do anything. I don't usually say x minus 0 to the 0 because that's just 1. But if you write it out this way, again, then you can see you're basically just in the formula. It's not harder to increase the formula because it just follows this pattern that you have. So then it was just a matter of trying to find these things. So f of 0 comes from plugging 0 into f, and you get 0. So if this is 0, I don't really care about any of the other stuff anyway, so I'm going to stop worrying about that. The derivative at 0, so derivative of sine is cosine, and the cosine at 0 is 1, so 1 times x over 1, plus the second derivative at 0. The second derivative is negative sine, so at 0, that's 0. 0 times x squared divided by 2 is still 0. Then the third derivative at 0. Third derivative would be negative cosine x. At 0, that would be negative 1 times x to the third over 3 factorial plus the fourth derivative at 0, which would be sine. Sine at 0 is 0. So times x to the fourth divided by 4 factorial is going to go to 0 anyway. And then finally, to get to a fifth degree, I need to find the fifth derivative. And the derivative of sine is what? The derivative of sine? It's cosine. So really, if we had to keep doing this, do you see how these derivatives would at least start looping? This is the same as the fifth derivative. This would be the same as the 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, since those derivatives just loop like that. Okay, so the fifth derivative at 0 would be 1 times x to the fifth divided by 5 factorial. So 5 times 4 would be 20, times 3 would be 60, times 2 would be 120, times 1 is still 120. That is where I came up with an answer of x minus 1/6 x to the third plus 1/20th x to the fifth. Hey, oh, I'm sorry. I did not even see you come in. I thought you were a student waiting for something. The leak is in the back corner near the pillar. I put a little bucket to start catching the water. But you can see, I think it stopped, but I don't know. Yeah. Okay, I'm sorry, was that enough for those of you that didn't get it right the first try? You see where that came from? Again, I think just a good strategy until you feel more confident in what you're doing. Force yourself to write out the full-fledged formula. I know x minus 0 to the 0 is just 1. I know 0 factorial is just 1. I know 1 factorial is just 1. But if you write it this way, and you just make some changes for the first order, make the same changes for the second order, make the same changes for the third order, then you can do that as many times as you need to for what order it is. Okay, so nothing specific to ask about this number 2? Okay, so again, this question 1 and 2 is a majority of what you will be asked to do. So just kind of scanning the other questions. 3 is the same thing, find a third degree. 4 is the same thing, find a third degree. 5 is the same thing, find a third degree. Question 6 is kind of the same thing, find a third degree, but instead of you finding all that information, they just give you the numbers to use. And your final answer should be an approximation at 1.1. Number 8, find a fourth degree. Number 9, find a fifth degree. Oh, this is a fifth degree, figure out what the coefficient would be. Number 10, this is the second degree. Yeah, so about half the questions are asking you to go in this direction, and about half the questions are giving you the information and asking you to backtrack a little bit. Yeah, Mason. I'm not sure. We'll just have to see. Right now you'll have 30 minutes. So use your 30 minutes and then I'll see where you guys are to know where we need to be by next class.
That's what I like.
Time to wait. Well, skip around if you want to. Some of the questions go the other direction. They don't feel the same. Girls, you have any questions?
The AV
Anything I can help with? Okay. You got anything I can help with there?
No, just the average, think about the 1 over 1 last year. Exchange for this, I don't think it's negative.
Yes, we go for
It's,
we just
it's also-
Yeah, so it would be a little bit, but.
You got any questions?
Yes, sir.
How many years have you worked at FHS?
Too many.
It's 50.
Wait, how many of them?
He's trying to estimate how many trees he brutally murdered.
What do you mean brutally murdered?
I mean, this year alone, I've estimated that you've given out 23,906 pieces of paper for homework.
Yeah.
I'm trying to estimate how many you've given out.
That's not a waste though. That's for your education.
It's a lot of
I mean, I guess I could make a classroom copy of this and y'all could just copy it all down the notebook paper.
23,000.
You're still using paper.
I started at FHS in 2012.
Is this your first place that you work?
Okay, well, yes and no. But so my first year at Fayetteville was in 2006 then.
That's, yeah, so 18. But how do you mean 2006 and then 2012? What's the?
A lot of people skipped the use Is this gonna be him next to us?
Maybe not the whole thing. I'm gonna wait and see how far y'all get. You still got about 20 minutes, so.
Yeah, but if you're looking at this term would be at times 2, 3. You need the. Yes, this is your coefficient, but you need the values of
Okay, we got about 15 minutes. Is anybody stuck on any of them? I can come give you a hint.
I'm lost. What's the Super Bowl?
I don't really like rap music.
What is the coefficient of x in the Maclaurin series for g? So here's what g is. So Maclaurin means it's gonna be centered at 0.
I wasn't watching.
So go ahead and start writing the first couple terms. And you only need to go out until you can see x. E to the f of 0.
Somebody or something look down this or something. I don't know what it is. Like his shop, everything was
Doesn't
different.
have to look through right here.
Oh, you're right.
So it's just gonna be 3.
Oh, and somebody else did the institution that drove.
Because our next,
And then, I don't know if it was Brazil that drove because it said, I don't know if you see what I said.
Yeah, so this is like x minus 0, this is x minus 0. Let me try to work it out too, because I remember I skipped that one.
It's different from the others.
Yeah, let me try it also, just so I can help you quicker. Bless you.
It wasn't interesting to watch, but it was funny to watch. Like the assumptions and features and features. I was happy to choose those. Did you see the celebrations afterwards that Philly was on? Yeah, they tore down like 2 or 3 traffic lights. Traffic and they were it's crazy. Like Philly has this one so there's a 2 mile. That's crazy. Right.
Check that.
Yeah, because one thing, and then like, if it was a challenge.
If one of those does not work, then you don't know if it
It's
dies.
exploding. It doesn't work. Fighting. And then somebody said Philly after the Super Bowl game, just no matter who knows. I mean, literally the one side by side with the 2 and 1. Then
Well, we know it's desolate. We don't know.
there were
that
any explosions. Doesn't converge.
Yeah.
The city was.
Yeah.
Illegal, that's.
Just positive and not
There's a fucking
choose the derivatives by doing that.
I feel like it people would say that.
Yeah. But I don't know how to do derivatives.
Okay, so this is F. And it's a uniform
Derived natural.
Here's F of 0, here's F prime of 0, times,
One over
you know, times the other stuff. And so this is just an X, I can see they're not subtracting anything. 1 factorial is just 1. So 4 is the derivative of F at 0. So that's what you need here. So I started writing out the Maclaurin series for G. So G is 0 over 0 prime plus G prime is 0 over 1 prime. I just started doing the formula. And then this is what they're asking you to find, the coefficient of X. So the answer came from G prime is 0. So here's G. Okay, is that? I took the derivative of G prime. E to this would be E to this times chain rule. And then at 0, I can plug that in. So that gave me E to the third times the 4. This came from that, and F prime of 0 is 4, and I got that from comparing that.
Max level.
Okay, so it's just the first 2 all that matter.
Well, what makes it hard is you kind of got 2 different things going on. You've got series for F that you got to pick out some information from, and then you've got to make your series for G so that you can see where your answer comes from, so you know what to find, and then you can plug this in.
Very easy.
Well, try it now while it's in your head, and then retry it again later.
What?
James.
What are we talking about? 41? Where do I not work?
You're not even on the same question.
Yeah, we're not working.
Anybody work number 11 yet? Okay. I like number 11. Did you finish that one?
Yeah.
Okay guys, we've got about 5 minutes here. So I need to give you a couple reminders that are on the bottom of the agenda, stuff that I've been telling you. Tomorrow's the last day that I could take ACTM money. And of course tomorrow's a B day, so I won't even see you. So if you're wanting to sign up for the ACTM, I need your $5, preferably tomorrow morning before like the 8:40 to 8:50. If you've not done your 10.1 to 10.5 quiz corrections, reminder that you can do that to get half your points back anytime during advisory, unless you're got a quiz or something to make up for me. Of course, that stuff's always going to take precedence. Or you can do it during a class period any day that you're done with what you need. Now, on this assignment, I'm going to only ask that you work through at least question 10, so you don't have to do more than through question 10 for homework. Just because this one's a little bit longer, I'm not trying to give you a ton of homework. Now, per usual, if you feel like you're struggling with this more than other people, then don't stop at question 10. Make yourself do a little bit more. And then if nothing else, you could re-practice a couple of those next time, and that's what's going to help you catch up to everybody else. But at least work through question 10. It looks like that's the people that stayed focused the whole time are able to get to that, and so they shouldn't have any homework. So I don't expect you to have past number 11, but my plan will be to come around and make sure that you have done through 10 to give you points that way. Keep you honest. Now, don't forget, there's no school Friday, so Friday is not an 8A, and there's no school Monday, so I will not see you again until next Wednesday. Please don't wait to do this homework. If you wait to do this homework, you're going to forget about it, and then you're going to lose out on those homework points. So you only have to get through question 10 before next class.